going to do any new thing. I'm going to do some review. Because one thing that we have not really discussed is how to find convergence of a series when you have all the various methods that could apply. Each time we had one single method in for homeworks, and so it's obvious what to do. So let's review first of all, what do we have for convergence criterions? Okay, so convergence tests. Tests for convergence. And then we'll discuss how do you know which one to use. It's not always obvious, but what should you try? How should you approach this thing? Okay, so the first one that we actually really talked about was the integral test. But as the word says, it involves taking integration. So it has to be something that you can integrate. The next one was the comparison test, but I only really covered the limit comparison test. So limit comparison test. Now in the limit comparison test, part of this is, if you want, the fact that we have two series that we know how they behave. The geometric series, so that there the condition was the absolute value of R, the ratio was less than 1, and we had the P series, and there the condition was that P had to be bigger than 1. And so the geometric series, just how does it look like? It was something of the form A R to the power n. The P series was something like this, 1 over n to the power P. You see the n is an exponent in the geometric series and is in the P series, it's a fixed number that is the exponent. Okay. In the geometric series we had a little bit more information, but I'm not going to talk about that now. Okay, that was the limit comparison test. Then we had the alternating series test. I'm listing the tests, but I'm not describing fully what they are, right? So there are some extra conditions sometimes. The alternating series test, but of course, as the name says, it works only for alternating series. And then finally, we had the ratio, and I put it between parentheses because we hardly ever use it, the root test. So these are basically the 4 tests that we have. Other than, of course, directly the P series or directly a geometric series. Okay, and today in the homeworks, I'm actually giving you a review sheet for the final, for the usual final. We're gonna do our finals slightly bit different. I'll let you know soon what we're gonna do. But most likely, I can tell you now, perhaps already, most likely, I'm gonna do the split the final in 2 parts. So the last week on Tuesday we will do 1 part, and on Thursday we will do a 2nd part. Okay. Because the material kind of splits in half, and the first part on Tuesday will be on the part that we did live, and the 2nd part will be on the part that we did online. Okay, so, but going back here, so this is what we need. So here are some examples of tests that we could look at, right? So we have seen, for instance, something like that, -1 to the n, let's see what I want to do here. 1 over n ln n cube. Okay. Sorry, I should mention this also. This is test for convergence, but we also have the notion of absolute convergence and conditional convergence, right? This was discussed in this topic here, ACCC, but of course it applies to everything. Okay, we can. Now for the integral list test and the limit comparison test, our series had to be positive. Okay, so we can use them. We can use these tests in the AC test. So we have already did some combination, but we haven't really combined the ratio test yet. So that's what I want to say. So here is one, and here is another one. Sinus 1 to the n 2n factorial over n factorial n factorial. Yes, okay, do this one. Another one I want to do is summation -1 n plus 1 square root of n squared plus 9 over the 5th root of n to the 12th plus 6n plus 1. Okay, so I'm going to work with the ACCC. I'm not saying that I always will ask you, but it gives me the most broadest approach to what can we do here. So for each of these 3 series, I will ask, what is this CC, is this conditional convergent, and or is it absolutely convergent? Okay. So let's look at what we have here. Now, how do I know what to use? Now, first of all, each of three of them are alternating series, and so we can use the alternating series test for it. Okay. Now, some of these things might be sometimes a bit difficult. So, yeah, sorry, I said that I was going to do ACCC, but I kind of let me be a bit more precise. Sorry, I'm retracting what I was going to say here. I'm going to ask the following things. For each of these, I'm going to be more specific. Okay, so that gets rid of this. And so I'm actually going to get rid of, sorry, give me one minute here. No, this one I want to keep. I'm going to get rid of this one. Okay, so for this one, I want to know ACCC. For this one, I just want to know convergent or divergent. AC, of course, or divergent. Here, convergent, divergent. And for this one, I again do ACCC. The reason that I make different here because the middle one actually is kind of hard if you have to do the alternating series test. Okay, so let's look at each of these separately. Well, these two here are alternating series, so we can definitely do the alternating series test on that. Okay, so that will take care of this question of at least part of the question. But for either one, I have to also check absolute convergence, and it means I have to ignore the negative sign. Remember, that's what absolute convergence means. Ignore the signs, and is it then still convergent? Okay, so if I ignore the signs, so I'm going to temporarily get rid of it, I'll get them back. And then what do I have left? Now I look at the type of problems I get. So you see the first one, let's look at our possibilities. Should we do an integral test, a limit comparison term, alternating series test is no longer valid, right? Because we are now got rid of the signs. So it's one of these three. How do I know which one to use? Let's start with the integral, not the integral test, with the limit comparison test. Somehow, I should be honest. I would always try to see whether I can use the ratio test, because it's somehow the most powerful of all. Unfortunately, for the first one, it's a very bad one. Somehow, if you have combinations of logs, and so it doesn't work. What is going to happen? I invite you to do it, but I'm not going to do it, is that if you do the ratio test, that you get a limit that is equal to 1. And that is the one case you don't want in the ratio test. It's the only case that is so-called inconclusive. That's the bad thing about it. But if you have something with factorials, there is absolutely no way that this is not the ratio test. So this is always a ratio test because of the factorials. Okay? Now the next one, it involves radicals and powers, and only that. There's no mixed stuff. So in that case, it looks like a p-series. It could have also be something that only consists of exponentials, and then it would look like a geometric series. So in that case, we should do the limit comparison. So what about this mixed form of the n's and ln's here? Well, as I said, a ratio test won't work. You can try it, but it won't work. Limit comparison test doesn't work either, because there's nothing to compare ln's with, right? In these two things, there is no ln's. Okay, so that's also out. If both of these are out, then you have to start thinking about the integral test. And so this is what it will be. This will be an integral test. Okay, so this is how you analyze the type of problems that you get. Now, I want to work them all out, so I'm going to get rid of all the blue stuff that I just did. Okay, and then, so let's work it all out. The first one, we have to do ACCC. So the first thing is, so let's call them 1, 2, and 3, right? So for number 1, I do the alternating series test first. That means I have to calculate this limit for n going to infinity. Now, remember, what you have to do is ignore the sign. So you get this quantity that you have to find the limit of. Now, this is extremely simple because it's 1 over infinity, so you get 0. Sometimes these limits might involve L'Hopital or something like that. Okay, so this means already that we have convergence, but we don't know yet absolute convergence. So now for absolute convergence, so that's not the question, that means we go look at the series 1 over n ln cube. Now, we already analyzed that we have no choice here but to use the integral test, because the ratio test won't work. Logarithms, for some reason, are not good for that, and it cannot be compared with anything. Okay, so I'm going to do the integral test. So integral test. So what does that mean? Well, first of all, it means that I have to be able to write this. It's going to be an improper integral from 0 to well, actually, sorry, I didn't say for where it starts. It should have started from 2, because otherwise I'm running problems the first two terms. So I'm going to start from 2 here. Yeah, these are small things that I'll make sure that they are correct in the test here. So here that we can start from infinity, and here we can start also from 0, and here 2. Okay, sorry about that. So here we have to start from 2, but again, it doesn't really matter what it starts from. Okay, if you rather write 3 here, do it, or 17, whatever. What matters, of course, is this infinity here, and then that we write here the function as a real function, so that we integrate. Okay, this always is an improper integral, so the first thing I do is make it a limit of a proper integral. Oh, x cubed, right? I forgot a cube. Now, of course, another condition of the integral test is it's not just if the other two don't work. I have to be able to integrate. If it's something I cannot integrate well, then I have to come up with something else. All right? So sometimes you can also very quickly rule out the integral test, because how are you going to integrate something with, how are you going to integrate this one? Factorials cannot be, x factorial does not exist as a function. I have to warn you for that. Also, this thing, no way that I'm going to come close to this thing for integrating. That is horrible to integrate, right? You know, what have we done? We have been able to integrate things that contain a radical of a quadratic. This is way more complicated, so forget it. Okay. All right, so we have to integrate. Now, as always, I like to do my integration first. Work it out separately. What kind of integration can I do here? You might be tempted to do isolate integration by parts, but remember, this cannot work if your functions, the transcendental functions, are in the denominator. Okay, so I wouldn't do it here. And so what works much better here is substitution. What is a substitution? Why do a substitution? Because ln x. Now, why not ln x cubed, you say? Well, the problem is if you take the derivative of ln x cubed, that is more complicated, and that's not just what you're left with. So I really have to take ln x, which is somehow the most inside you can be. Then du is 1 over x dx, so it's a bit of review of integration here. And so now we can replace 1 over x, so let's make everything, so this is 1 over x dx, that is this part, right? So this will be just du, and then everything else, this ln x here is now to the power 3, so this is u to the power 3. Oh, whoops, in the denominator, of course. Yeah, be careful, I saw some people do mistakes also. If it's in the denominator, it stays in the denominator, right? Okay. So this is u to the minus 3 du. I write it in power because I have to do the power rule. Remember, add 1 to the exponent divided by the exponent plus c. And then u was ln x. So it's ln x to the power negative 2, which means really 1 over 2 ln x squared. Okay, so u squared is the minus 2 means that it's u squared in the denominator. And now I'll replace u by ln x. And there's a negative sign that I should not forget. Okay. Plus c, but the plus c I don't need because I'm going to use here in the in the fundamental theorem of calculus. So it's limit t going to infinity of minus 1 to ln x squared between 2 and t. So what do I get? I get minus 1 to ln t squared. I still have a limit here. Sorry, I forgot to write my limit. Minus 1 to ln 2 squared. That's the other endpoint. Now, this number, I really am not interested in what it is. It's a number. I'm happy with whatever it is. What it matters is this part, because this is the limit part. And because in the integral test, and many of you made a mistake on the quiz, in the integral test what you need is not infinite. As long as the limit exists, it doesn't matter whether it is 0, less than 1, bigger than 1, whatever. It means convergent. In this case, what happens if I plug in? Well, the ln of infinity is infinity, so I get 1 over ln of infinity, so 1 over infinity, so that is 0. So this thing is 0, and this thing is whatever it is, it's 1 over 2 ln 2 squared. So we get convergence here. It doesn't matter what the value of this thing is. Okay, don't make that mistake. So conclusion now, the conclusion is yes, we have absolute convergence, because even if I ignore the sign, I still have convergence. Remember, this also meant that we actually didn't need to do this. We could have skipped that, but you sometimes don't know, so it's better to do it. And at least you get partial credit if you cannot do the rest. Okay, let's do number 2. Number 2, let me copy it again. How was it? It was 2n factorial, n factorial, summation, 2n factorial, n factorial, n factorial. This one, because of the factorials, it can only be the ratio test. So the limit for n going to infinity. Absolute values are not necessary because everything is positive, but I still write them to remind you of them. That's what you get just copying. Now I have to replace n by n plus 1. Okay, so 2n becomes 2n plus 1. And this whole thing gets a factorial. And then you get n plus 1, and this whole thing gets a factorial. And here n plus 1, and the whole thing gets a factorial. See the parentheses. If you forget the parentheses, you might know what you mean, perhaps now, but if you look at your notes later on your homework or solution, something, you can say, what the hell was that? Okay, so use these parentheses. Okay, let's simplify this now. So, as I said, no need for this absolute value signs. This one, let's expand it. It's 2n plus 2 factorial. Then we have the n plus 1 factorial and another n plus 1 factorial. And then this 2n factorial goes here, and these two guys come up. And then the whole thing is that you look at, for each of these three groups, what is the biggest factorial and how can I write a smaller factorial in terms of that? The simplest one is, of course, the n plus 1 factorial. That is just n factorial times n plus 1, because you have to go one more. The little bit more complicated one is this one, 2n plus 2 factorial. And I have to go to 2n factorial, right? I have to write the biggest one in terms of the smallest one. So 2n factorial. Sorry, I should actually have put parentheses there. I forgot to copy them. 2n factorial. So now, from 2n you have to go to 2n plus 2, but in steps of 1. Well, the first step is this one, but I'm not there, so I have to write another step, 2n plus 2. And what steps, of course, means each time multiplying with that number. Okay, we're done. So we can rewrite our factorials now. The last one we just did is 2n factorial, 2n plus 1, 2 times n plus 1. I'm going to factor out the 2 because I know already what is going to happen. And factorial, n factorial. We have a 2n factorial. Then the n plus 1 factorial was n factorial times n plus 1. And the other one was the same. Okay, so this is twice using this formula. All right, we have a lot of cancellations. These factorials, all the factorials have to be gone. Otherwise you did something wrong. That's the first thing to notice. But also, since I already factored out the 2, it's now clear for me that I also can factor out that one. This might happen or might not happen, right? We're lucky here somehow. Okay, so what are we left with? Limit for n going to infinity, we get the 2 here, don't forget the 2n plus 1 over n plus 1. So we divide top and bottom by the highest degree, or you can do L'Hopital. So this is n here, and n here, and n here, and n here. And you get limit for n going to infinity. We have 2 times 1 plus 1 over n. No, 2 plus, sorry, there's a 2 here. 2 times 2 plus 1 over n over 1 plus 1 over n. And then we use the fact that these guys are equal to 0. And what we're left with is 2 times 2 over 1, so 4. This is bigger than 1, so this means divergent. Okay, so that's Dubik. Alright, that's number 2. And number 3, that's number 3. You know what, number 3 is, I'm gonna copy the wrong if I do this, so I'm just gonna erase this part here. Okay. I have still not found the fastest way to erase everything, so you see me keep going up and down here. Okay, I need more space probably, but I will make it if I need it. So okay, it's again, so number 3, step 1 is the alternate series test. Now this is a little bit trickier. Okay, because I have to now calculate the limit for n going to infinity of what? Well, of this quantity without the negative sign. So n squared plus 9 over 5th power of n12 plus 6n plus 1. Now, don't confuse this step with the next step. In this step, since it's a limit, I have to divide top and bottom by the same quantity. And some of you did this wrong on the test and they concluded divergent, and you lost almost all points because it really skipped almost everything. So here we have to make a choice what power we use. So let's write down what are the powers here. This would be the cube root of n squared. If you write it in exponents, it would be 2/3. And this one would be the 5th power of n12. That would be the highest, right? We have to keep the radicals as well. That would be n12 divided by 5. That is a bigger number, right? This is 2.4, I guess. And the other one is less than 1. So this is the number that we should divide by. So we're going to divide this by n12 to the power 5, or if you want the square root here. So, okay. Now this is a little bit trickier because I have to bring this guy inside there. Well, how do you bring a power inside a radical? Well, you have to raise it to the index of that radical. So this will become inside. I have to keep erasing a little bit here. Let me get a little bit more erased. Okay. So I have to bring this, so inside the third radical I have an n squared plus 9, and now I have to bring in this guy, so I have to take the third power of it, that is 36 over 5. Multiply this with 3, because if I now take the third root, then I will get this guy. Do you agree with that? Okay. In the bottom, it's easy because there it's a 5th root anyway, so it goes just in there, right, as n to the 12th. It's the same thing. You multiply this with 5. Now I bring it in 5th root, I multiply with 5, so it becomes n to the 12th. So we get n to the 12 plus 6n plus 1. And inside we have an n to the 12th. Okay. Let's see what we get here. What are our powers? And we always look at the highest power, right? Well, sorry, I mean to say we always write it as reciprocals now. Now here this is 2 and this is 36/5, which is way bigger. So the whole thing is 1 over n, subtract 36/5 minus 2. So this power here is 36/5 minus 2, right? That's how you divide here. So which is 36 minus 10/5, which is 26/5. Okay, so that's where I'm going to write this now. So 26/5 plus 9 over, well, 36 fifths. Okay, and in the bottom, okay, I need my space so this calculation goes. In the bottom, I get fifth root of 1 plus 6 over n to the power 11 plus 1 over n to the power 12. Now, all the reciprocals, they all have positive powers, so they all go to 0 here. All this is 0. So the only thing that is not 0 is this 1 here. And so we get actually 0, because on top everything is 0. That's why we get 0. Okay? And this is what we want. So we get convergence. Okay. What about the step 2? AC, we said we have to go to do limit comparison. And now comes, so it's now becomes, so let me write again what it is that which is the series that we're looking at. For the absolute convergence, we ignore that negative sign here. Okay, we're going to ignore the negative sign, so we are talking about this series. Cube root of n squared plus 9 divided by the fifth root of n 12 plus 6n plus 1. Okay. So, in the limit comparison test, what you build is a Bn. And the Bn consists of the top power, the highest power in the top, which we already discussed here, that was this one. Okay, so third root of n squared. And the bottom one was this one. And remember here, it's better to keep your radicals. Fifth power of n to the 12th. Okay. And then what we need to show, before we go any further, we have to show that this limit, here, limit of an over bn, that this is not 0 or infinity. So that's the next thing we have to do. This guarantees us that we made the right choice. But I need to see this work. Even if you made the right choice, I need to see this limit. Okay, that's always going to be part of, so don't skip that, because you're not going to get a full credit then. Okay, so we have to calculate this limit, and this how we did this on our very special way, right? We took the numerator of an and divided by the numerator of bn. And we did the same with the denominators. Okay. We did this because in that case we have everything under the radicals as we want. We have a third, we have an n squared over n squared plus 9 over n squared. Remember, when you divide, you have to divide every single term. Okay, well, if you think, wait, perhaps you're going to complain and say, what are you doing here? So let me do it one more step. So what I do is I put everything inside the radical. That's what I meant. Let me do it in 2 steps, otherwise. N to the 12th plus 6n plus 1 divided by n to the 12th. Okay, and now we can work out these ratios. So we get the cube root of the n squared divided n squared 1. 9 divided by n squared, that's what I was trying to say, right? Each single term has to be divided. And in the bottom we get a fifth root of 1 plus 6 over n to the 11th plus 1 over n to the 12th. And in the limit, as before, right, you see the limit is very similar, but still, all these guys go to 0, and we get 1 over 1, which is 1. Is this less than 1, bigger 1? No. This is what we wanted, so this is okay. But that's not the end of the story, because now the last part is we look at Bn. What is Bn? Well, it's a P series. Let's write down what it actually is. 2/3. Remember, if you don't make a mistake here in the writing the exponents, right? This is the power, is always the numerator of the exponent. The index of the radical is the denominator of the exponent. Okay, so here we have 12 is the power, 5 is the radical. We have to write this in the bottom. That's how P series are written. So we have to write this as 1 over n, and then we have 12 fifths minus 2/3. So let's work out this number. So P is 12 fifths minus 2/3. And we have to see is the bigger one or smaller than 1. So best thing is to put a common denominator 15. 36 minus 10 over 15s. You see that, right? Multiply 3, multiply 5, 5. and that is 26 over 15. That is bigger than 1. And that's the only thing that matters, so we had, again, convergence. Now, this again means that we have absolute convergence here, because without the negative sign, it even converges. So even here, we needed not to do this step 1, which was actually an awkward step to do. So you could sometimes try to do first the second step, and if that works, then you're done. If it's not, then well, you have to do step 1. It depends a bit. Sometimes, in this case, the alternating, I didn't need to do the alternating series, but it was so simple that I did it right away. So, by the way, so this was the answer here, and this was the answer, right? Just, okay. So this is a review of the different tests that we have for convergence. So this is, call it review on series. We should also do a review on power series, but I'm going to wait with that, because otherwise it's a bit too much. And so, I probably I have to think about this, but probably I'll do a test also on this thing here. We kind of did a test like this, but I might want to do perhaps another one. A quiz, a quiz. No, test a quiz, okay, get confusing, right? All right.